Okay, welcome back. An introduction to programming with Python, lesson 3. Now we're going to look at today a familiar and important structure in programming, and that's a loop. In particular, we're going to look at a while loop. The way a while loop is, well, it starts off with a while, and then there's a logical condition. And as long as that logical condition is true, then while that condition is true, we're going to do something. And there's going to be a set of instructions that are going to be carried out when this logical condition is true. And those instructions, you'll recognize them because there's an indent of 4 spaces or 1 tab space. So here's a simple example. It's not really a very practical example, but it'll show us sort of how the loop works. We set the value of I to 0. Then we say, as long as I is less than 10, carry out these instructions. And the instructions will be the indented ones. So these will be carried out repeatedly, as long as I is less than 10, and will eventually, hopefully, reach the condition where I is not less than 10, say maybe when I equals 10, and then the loop will finish, and then we'll proceed next to the non-indented instruction, and so on, down through the rest of the code. So, in our minds, what's going to happen here? I is 0. So is that less than 10? Yes. So carried out the indented instructions. So what are the indented instructions? Okay, it's going to print the word loop and then the value of I, which is 0. Then, this looks a little odd. We're going to take the old value of I, add 1, and then store that back as the value for new I. So 0 plus 1. So basically, we're changing the value of I from 0 to 1. The indent ends here. So control reverts back up here to this statement. Is 1 less than 10? Yes. So it's going to carry out the indented instructions again. So it'll print loop 1, then it'll take 1, add 1, and it'll make I equals 2. Then we go back up here and say, is 2 less than 10? It is. Print loop 2, add 1 to I, and so on and so on. Now the last one is interesting. When I is 9, it'll print loop 9. It'll add 1. It'll get 10. So I is now 10. When it goes back up here, it'll say, is I less than 10? No, it's not. So it won't do those 2 instructions. It'll come down here, and it'll just print the loop is finished. So if we save this and then run it, you see that I goes up to 9, and at that point, the loop is finished. So when do we use something like this? Well, there's often times where we're studying the motion or behavior of a system, and we want to analyze the motion up to a certain point and then stop. So an example of something like that might be a free fall problem. So G is 9.81, and let's set the velocity to 0, and let's set the height to be, I don't know, 100 meters, let's say. And then we'll say, as long as I'm above the ground, as long as Z is bigger than 0, carry out these instructions. So what are we going to do? Well, we're going to let it speed up a little bit. So the new speed is the old speed plus the acceleration, which is minus g, times multiplied by time. Now, for my dt, I'm just going to take a very small time step. I'll put it up here in my constant of 0.01, let's say. So, my initial velocity plus acceleration times a small time, that's my new final velocity. And the other thing I'm going to calculate is I'm going to calculate my height. My new height is my old height plus my velocity times time plus 1/2 times my acceleration multiplied by time squared. And this is to the power of 2, star 2. Okay. And then perhaps I might want to just print out, whoops, let's spell that properly, print Z. Beware, it's going to print out an awful lot. Let's just make Z equals 10. Otherwise, this is going to take a tremendous amount of time. And then let's say I'm finished with that loop now, so I'm going to delete to go back to column 0 there. And I'm now going to say print the impact speed, because I'm now at the ground, and that'll be v. So this should be the last final velocity I got when I reached the ground. So as long as we're above the ground, d is vit plus half at squared, vef is vi plus at, so go a slight step in time and see what your new position is and your new velocity, and then when you're no longer above the ground, then you've hit the ground, and then we want to know what our impact speed is. So this would be, a typical physics while loop. So again, as long as z is 0, these three instructions will be carried out. When z is not greater than 0, i.e. when we've hit the ground, then this instruction will be carried out. Okay, just let me get rid of my previous loop here because we don't want to necessarily do that one again. I'll just comment out all of these. Remember, putting the ampersand means that the interpreter will not execute those statements. So these are the only ones that are going to be executed this time. So let's save it and run it. And it's going to print out quite a few values. Look at all of them there. And those are the z's for each little time step. So we started at 10. And you see we weren't going very far at the beginning. Well, because we were still not moving very quickly. The object was just released from rest. As time goes on, we start getting closer and closer to ground. And then as the speed picks up, you'll see the distance increments are greater. And then eventually, here we go. Right down here at the last one, we hit the ground. And then that was our speed at impact. So that's a typical use of a while loop in physics. And this you would do if you had a really complicated acceleration. Of course, we know that we can just solve this using physics 11 with a height of 10 and an acceleration of downwards 9.8. We can calculate what the impact speed is. But we did it here using a small time step. First of all, to show you an example of a while loop. And second of all, if you had a complicated acceleration that wasn't constant, then this method of using a small time step to move through the motion is a time-honored technique in physics. Now, there's one other example we're going to show you of a while loop that involves finding the root of a function. And that's a slightly more complicated example. Let's look at some graphs here. Let's look at the graph of sine x and x over 2, just as an example, and pretend we wanted to know where those two graphs crossed each other. Now, one way to do that would be to look at the function which is y1 minus y2, and just see where that function actually goes through 0. And that will be where those two things equal each other. So this is an equation solving technique, because this could be the right-hand side of any equation and this could be the left-hand side of any equation. And we can use the techniques of finding the root of a function to solve this equation. So how are we going to go about finding the roots of a function? There's several techniques in numerical methods, numerical analysis, one of which is called bisection. And the way that that works is you start off sort of bracketing the root. You look at the graph and you say, okay, it's between this value and this value. Now you notice that the function has to change sign as it crosses the root. So here it was positive and here it was negative. And you use that property of the change of sign to try and narrow in on the root. So for instance, what you do is you start with two values, say like 1 and 3, and then you look at the midpoint, which would be 2. And then you find, where is the change in sign? Is the change in sign between 1 and 2? Yes, it is. Or is it between 2 and 3? Well, there's no change in sign between 2 and 3 because the y value is negative and negative. Here's the change in sign. It's between 1 and 2. That means the root has to be somewhere there. So then you proceed again. You divide this interval in half, so you go here to 1.5. And then you say, on which half interval does the change of sign occur here? Well, it doesn't happen on this side because y is positive everywhere here. It happens here between 1.5 and 2. So now I know the root has to lie between 1.5 and 2. So this is a process that you can repeat over and over and over again. Divide the interval in half and then ask, on which half does the y value change sign? Because that's where the root has to lie. Now the reason that this is a good procedure is that you can automate it. You can make it into an algorithm, and computer programs are great places to run algorithms. And you could do this iterative process of dividing the interval in half. You could do it 1,000 times, and you can get extremely close to this value. Now by eye, we could maybe do it 4 or 5 times and then be satisfied with it. But of course, that is not necessarily all the precision that we would want. So computer programs are really good at calculating and solving these equations precisely. And the tolerance is actually something that we can set. So for instance, we could say we want to know that root to within 0.001. And you could, for instance, want it 1 part in 10,000. Really, with all the bits that we have at our disposal, even in a laptop these days, we can solve these solve these equations quite accurately, solve for these roots. Now you'll see here I've already defined my function. It was sine x minus x over 2. The sine function's in the numerical Python library, which I imported up above here as numpy. Numpy is np, rather. So there's our function. And we're going to have to start off the search for a root with a left and a right. That's my original interval. So we'll use the input command to ask for those two. And now what we want to try and do is explain in very simple terms to the computer what our algorithm is, because computers aren't smart, it's people that are smart. So how do we go about putting that algorithm into steps that a computer can execute, and execute repeatedly? So you can see we're going to need a loop. Okay, so this is how the algorithm is going to work. We're going to have a function, it's going to cross the axis, we're going to have a left and a right limit for x, and the root's got to be somewhere in between. So what we do is we calculate the midpoint halfway between left and right. Calculate that midpoint. That's easy to do. It's just the sum of the two values divided by 2. And then we ask, does the sign change happen on here or on here? Because we've divided the interval into 2 parts. Now, clearly, it's going to happen over here, because here we're going from a negative y value to a positive y value. The root is on this side. So all we do then is we say that I'm going to now drop this as my left end. This is now going to be the left end of the interval. And then we repeat. So because there was no sign change here on the left side, I set my left to be where the mid was. Now I repeat. I divide the interval in half. It's now, the midpoint is now right here. And then I say, okay, is the sign change here? Yes, it is. So because the sign change is here, what I am calling right, I'm now going to change. It's now going to be this point. So here's my algorithm then. I'm going to start with left and right. I'm going to calculate the midpoint. And then I'm going to find the y value there. And then ask, is that bigger than my tolerance? Which, we could set to be 1 part in 1,000. Now, the other thing is we're going to have to take, is the absolute value bigger than my tolerance? That would mean that I'm not close enough to the root yet, because I want the y value to be smaller than not at 1 on either the positive or negative side. So, while the y value at that midpoint is bigger than tolerance, that means I want to get more precise. So, what do I want to do? Well, I want to try and figure out, is this on which side of the interval is the sign changing? On which side of the interval is the root? Is the root on this side or is the root on this side? And the way I determine that is again by the change in the sign. So what I'm going to say is the sign of f mid, is it equal to the sign of f left? Because if it is equal, that means there's no change in sign between those 2 points, and that means that the root doesn't lie on this side of the interval. And if the root doesn't lie on that side of the interval, then I can reject my old left value and make this my new left value, because I know I have to look over here for the root. So if this is true, if yes, then my new value of left should be mid. If not true, then my new value of right should be mid. And then, having found a new left and a new right, I would once again calculate this midpoint. And then I would once again ask myself the question up here, is the y value at that new midpoint, is it still bigger than my tolerance? Am I still farther away from that root than I would like? If so, repeat the process. At that midpoint, decide where the sign change is, reset your left and right, calculate the new midpoint, and then again ask, is the y value at that midpoint bigger than tolerance? When this loop ends, the y value is going to be less than 0.001, i.e. we're going to be very close to the root. So this algorithm should enable us to find the root and to solve the equation to an arbitrary precision, because we could come back here and we could add extra zeros there if we really wanted to. So now we just need to convert these words, what's called pseudocode, into actual code. So we'll bounce back and forth between these two now. So you'll see I've already got it programmed here a little bit. We're going to ask the user to look at the graph and to find left and right. I mean, we were talking about 1 and 3 earlier as being good inputs. So you're going to calculate the midpoint. Then you're going to say, is f at the midpoint bigger than tolerance? And tolerance is a constant set up here. Now, the one thing I need to change here, of course, is we need to take the absolute value, and the absolute value function is in the NumPy library. So is the absolute value of this function, is it greater than tolerance? If it is, then we ask a question. Oh, sorry, I shouldn't say if, I should say while. It's a while loop here. So while that's bigger than tolerance, then I ask a question. Okay, I'm going to say if the sign of f, I'll use some spaces there, of f mid equals the sign, and the sign is found in the numerical Python library, of f left. If that's true, just make a comment, then there's no root in this half interval. And then, so if that's true, what do I want to do? I now want to set left equal to mid. If it's not true, else, then I want to set right equal to mid. So when all of this loop is done, I should be really close to the root, and so I just want to print out the value of mid and f mid, and then close. Now let's just comment out all of this stuff above here, because I don't want to do this anymore. That was my first example of a while loop. I've now done one that's quite a bit more involved. Okay, so that's all commented out, and now I'm just going to do this, and my code always works right the first time, ha ha ha. Okay, so it didn't like that, so let me figure out what was going wrong there and fix it. And actually, let me expand this a little bit so we can see what was going wrong here. So it didn't like that logical statement. Okay, just let me correct my syntax. Okay, so found that mistake. Here it is right here. Equals is an assignment operator, but to check for equality I actually have to do equals equals. So now this should work. So let's save it and run it. So it's going to ask me for the left bound and the right bound, and then it's going to go through its iteration again and again and again, and then something must be wrong because this loop isn't ending. This is a sign that it's caught in an infinite loop. So there's still something wrong with this code. Let me pause it and then get... Okay, so yes, I found what was wrong with that code. You remember back here in my pseudocode how we had to recalculate the mid after we'd set the right and lefts? Well, that's what I was missing. I missed that the new mid will be right plus left over 2. And I put in a print command here just so I could see it actually iterate. And so when I did that, So here's my while loop. Here's where I ask the question. Here's where I recalculate the mid. So you see I went through the loop exactly 1, 2, 3, 4, 5 times. Let's see how many times we have to go to the loop to get the root to within 1/10,000th now. So when you're having trouble with your code, it's customary to put print statements in there so you can output variables and see what's happening. So you see here was right and left, so this is the interval that contains the root each time, and you see how quite quickly we narrow in on the root. So I'm already there, 1.89, 1.89. I've already got it within 3 decimal places, and I only had to iterate that process about 10 times. So it's a very powerful technique for finding the root. It's called bisection because you cut the interval in half, and then you just ask the question, where does the sign change? Does it change on the left half, or does it change on the right half? And then you throw away the half where there's no change in sign. So there's the algorithm, and that takes a little getting used to and a little understanding, but this was meant to be a good example for teaching a while loop. And we were just running this loop over and over and over again as long as the y value was bigger than my tolerance. As soon as the loop stops, the y value is less than my tolerance, so that means that we're really, really close to the root. So you can see my y value here is 1 times 10 to the minus 5. Indeed, quite close to the root. So those are a couple of places where you might use a while loop. This is sort of a numerical method to find the root of a function. And then back up here, we did another numerical method where we did a small time step through the equations of motion so we could analyze where the particle was and how fast it was going as a function of time. Our very first example of a while loop was a trivial example just to show you how it worked in terms of the logical control and the sequence of steps. So that is the while loop. It's an extremely important structure in programming.